네, 안녕하세요. 한성민 씨, 정상복 씨, 박건우 씨. 네, 질문 있으면 질문을 해주시고요. Okay, so let's get started. This is lecture 25th. Okay, so we have only 2 remaining lectures and we will talk about additional topics for computational microelectronics. And the final term project will be announced in the last lecture. Okay, so now let's get started. So today we'll talk about the capability of mixed mode simulation. So the terms called mixed mode means that, yes, so usually up to now we have simulated the behavior, electrical performance of our MOSFET or PN junction, whatever, one single device. However, in reality, the device is not uh, there alone. So of course it is always connected to other circuit elements. The thing we have assumed up to now is, okay, so although that is the case, but we can think about one specialized case like gate bias and drain bias is directly applied to this device, and we can measure the response of this device. Usually we just measure the terminal current as a function of terminal voltages. That was usual situation. But now sometimes we can try to do a little bit further than just a single device simulation. So the mixed modes means that when they just coined this name, so they say that they means that the previous researchers on this field just thought that, okay, we have a device simulation and we have circuit simulation. So these two capabilities are merged into one simulation. So this is just a mixed one, not entirely for device, not entirely for circuit, but it is just a mixture of device and circuit. For example, let me just consider a simple example. Yes, for example, let's say that here we have a certain resistor, and let's say here we have another transistor. Yes, so you have seen it in your previous courses like microelectronics. And yes, we just apply certain voltage and measure output voltage as a function of this operation of this circuit. Okay, so how can we actually calculate this V out? One way to be done is just to obtain the property of all of this MOSFET. So once we know this I, drain current, as a function of gate source bias and drain to source bias voltage, then once we get this table or anyhow certain um, model for this transistor, after that we can apply the Kirchhoff current law. So for example, let's say that this is a VDD, then when we apply the Kirchhoff current law to this node, then we can immediately understand VDD minus V out divided by RD, which is the current flowing through this drain side resistor, should be balanced with ID, VGS, VDS. Yes, so by solving this simple KCL, then now we can get certain solution for our V out, and that will eventually, when we consider the of when we consider a pair of VGS, comma VDS or V out, then we will have input and output characteristics of this single NMOS inverter circuit. Okay, so that is the situation. So if you have only capability to calculate the device, a single device only, that is the thing you can do at best. But point is, when we consider this mixed mode simulation, you just include this procedure. So solving the KCL at the same time is merged into your simulation capability. So now when you have a mixed mode simulator, then you don't have to individually calculate this ID versus voltages relationship. You just generate certain circuit schematic contain both of transistor and resistor, and just let the simulator solve it. Then automatically you will get the answer of your circuit operation. So that is the thing we can get from mixed mode simulator. Okay, let's think about another case we are interested in. So for example, let's think about this guy. Yes, now we have this one. Yes, we have a capacitor, and here we have a transistor. So let's say this is M1 and C1. Yes, and initially let's say that at time equal 0, the initial potential for this node is non-zero. Let's say that certain positive value. After that, now we just connect it to the ground, and what we wanted to know is just to calculate what happens to the voltage of this node. Okay, so of course when you have full knowledge on this transistor, then you can always calculate this V as a function of time. How can you do that? In this case, what you have to do now is not this KCL, but you have to introduce a little different of KCL. So that is simply given by once again KCL, but here in this case C times C1 times dV over dt. That is the capacitor current, okay, and that should be also balanced with drain current, and drain current is simply given by once again drain current as a function of, once again here we have to have gate bias and drain bias. However, in this case drain bias itself is just can be written as V over T, and we assume that this is a given number, yes, given voltage. So typically in many cases we just set this value as a low value, so transistor is assumed to be turned off, and ideally there will be no current at all. So if this is the ideal case, then what we will get out of it will just looks like this. Yes, as a time elapse, so voltage of our capacitor is just kept as before. So although time elapse, so there will be no change in this capacitor voltage because there is no current flowing through M1 transistor. But that is just an ideal case, and unfortunately in our transistor we can find many uh, um, non-ideal effects. So even though we have applied very low gate voltage, so still we can have leakage current. Then maybe we will find that there will be certain degradation of our voltage level, and if this level is go behind or go below certain level, for determining whether this value is high enough or low or sufficiently low, then actually that is related with the change of the bit. If we interpret this sufficiently high voltage as a logical high, logical 1, and if we treat it as a logical low, logical 0, then that means that bit flip happens to this case. So that is quite important for realistic case. So once we know, for example, if we let's assume that you have just the capability to simulate the property of performance of M1 transistor only, then what you have to do is first start from time equal to 0 and calculate the current ID of your transistor, and after that just to assume that what will happen to time equal 0, and after a small time difference has passed. Okay, so since the transistor is more or less the initial transistor bias condition, so maybe we can treat this IDE as a constant, so we can imagine that the voltage will be only small, uh, uh, the voltage will change quite small. So after time delta t is passed, then what will happen? Okay, the gate voltage is kept as before. However, due to this small leakage current, so in this case our t v at time delta t is now given by the t equal 0, the initial value minus mm, times, okay, so let's just write down more rigorously. Okay, let's consider charge. So initially we had a charge corresponding to this one. However, we just have loss of charges due to this leakage. So what we will have is just ID calculated at time t multiplied by time distance delta t. So that will be the value of our C times V delta t. Yes, that will be the case. Now, once you calculate this number, oh, then what you can do is, okay, now we have this number. This number, the voltage of capacitor is identical to our VDS. So what you can think is, okay, the drain voltage is slightly lowered, so leakage current can be slightly lowered. So with this one, now you can also treat another step. For example, let's say C times V of 2 times delta T is simply given by C times V delta T minus ID of V ID of delta t times once again delta t. Then how can you calculate this number? Yes, you can just have a fixed gate to source voltage, and VDS in this case should be regarded as V of delta t time instance. Okay, so by repeating this procedure, also we can make a certain approximated value for our capacitor voltage. Okay, so that will be just behavior of your data data retention and characteristics of your DRAM cells. This is nothing but just a certain DRAM cell, one transistor and one capacitor, and the figure just shows that how the transistor uh, can act as an leakage path for your DRAM cell data. So okay, so do you have any question up to now? So if you have any question, then please let me know. So of course, if we have only capability to calculate the property of our transistor only, that will be the best thing we can do. However, what happens if we can just consider the combination of a transistor and capacitor? If we can do it, then things becomes much more easier. So everything related with this KCL calculation is just done by our simulator, and as from the user point of view, the user only can just let the simulation go, then collect the data. So that is the power of mixed mode simulation. Okay, so simply speaking, compared with actually the transistor simulation, so solution or techniques are used for this drift diffusion model, actually considering the KCL is not that difficult. So from the viewpoint of implementation, it's relatively easier than the implementation of a drift diffusion model. However, the difficulty or easiness of implementation does not guarantee that the usefulness of your code. The usefulness of your code is determined by users, not by the developer. Although the developer has spent quite a lot of time on certain capability, if nobody is using it, then yes, its usefulness is quite low. However, to developers, it can be just a simple modification and can be regarded as just trivial, but in many cases, users, that is the right thing to be implemented, and the usefulness is really high. So, so from my point of view, actually mixed mode capability is quite important for the realistic device simulator. So now today we will talk about how can we implement this mixed mode simulation. Okay, if you have any question on this stuff, then please let me know. So up to now, I just gave you the motivation why we have to consider the mixed mode simulation. So why we are not much satisfied with this single device simulation. Mhm. Okay. No, so Mr. Park, I just introduced C times V in order to consider the charge Q collected at the capacitor. So single side of capacitor. So when you have C times V product, so it just shows that how many charges are implemented or collected at this point. Yes. So what I have done was just to CV at time equal delta t. So this is the charge collected at the capacitor node can be, so this is can be regarded as a charge at t equal delta t can be written as c times v t, the original or initial charge minus id 0 delta t is, that is corresponding to charge loss due to the ammonia leakage current. Okay, so once again, C times V is just introduced to have the charge at the capacitive node. Okay, Mr. Park, so are you with me? If you have further question, then please let me know. Okay, then now let's think about the mixed mode simulation. So in the case of a mixed mode simulation, we assume that we can perform the single device simulation. That is done. Then how can we consider this additional circuit elements? So that is done by today's lecture. Yes, let's think about two circuit elements connected to each other. Yes, and yes. So that is quite typical in our case. Of course, although I have used the ground and VDD for showing the typical value, but it is not quite necessarily to be ground or VDD, because we can have a certain level. So also here I just drawn two terminal devices, but even in this case we can introduce additional terminals, and additional circuit elements can be connected. The point is, let's think about what happens to this node where two or multiple circuit elements are meeting together. If we have a certain node, this is a circuit node, and in this case we have to introduce the KCL. Yes, now we have to solve the KCL. Then what is the KCL? So KCL is simply the sum of incoming current should be balanced with the sum of outgoing current. So when we just uh, write down the branch current in a unified manner, then actually the sum of branch current should be 0. That is the KCL. So please note that in our field, usually we take the convention for our terminal currents like this. Always terminal currents are defined as from external node into the our device. So from the viewpoint of our circuit node, so highlighted as yellow color in this case, then every terminal current is heading just outgoing way. So what we have to do to calculate KCL is quite simple. Just to make a sum of related branch. So for example, yes, it can have two branches and they have their own terminal current, and sum of our terminal current will give us just 0. It is simply because every terminal current is well aligned to our directional convention. So everything is just outgoing from the viewpoint of our circuit node. So just to make the sum of them will give us just 0. So I said that's it. That's it for our KCL implementation. Okay. So simply speaking, you have to introduce one single line for your residual vector, and that should have, for example, let's just say that this is element 1 and element 2, and it is given as a terminal 1 and terminal 2, terminal n and terminal 2. Then what you have to introduce in this case as a KCL is just I of your first element and its second terminal current, and plus I2 second element and its first terminal current. So this one is corresponding to, in our graph. So this is corresponding to this guy shown here, and this one is corresponding to the one shown here. Yes, this guy. The sum of them should vanish. This is the KCL applied to this node. Okay. So up to now, I have just shown you how can we implement the KCL into our system. So previously we have made a certain drift diffusion code, and we can just introduce this single line to consider the KCL. Of course, we have to provide the information for the element 1 and element 2. So both of them can consider multiple lines or multiple equations for them. However, the additional information we have to introduce to connect them is just KCL. Okay. Then let's go to really simple case. So up to now I have introduced a very simple rule. Then let's just consider the simplest thing we can imagine. So in this case, and both of the element 1 and element 2 happen to be just registers. So let's say that this one is R1 and R2. So then how can we write down this KCL? So this is the same as before. So let's just consider, yes. So we can consider two terminal and two terminal currents and two terminal currents heading in this way, So for this node, then for KCL, what we can write down is quite simple. So I over R1 and its second terminal. Let's just say that this is a second terminal and first terminal and second terminal and first terminal, for example. Then that will be also R2 and its first terminal should be 0. That will be the only thing we have to additionally introduce to our system. So this is nothing but just KCL. Then obviously that's it. But let's think about the real implementation of this system. Once you just introduce this KCL, of course, this system is not determined because we have introduced two variables, and yes, there is only one single equation. So what we have to introduce is then what is R I over R1 divided and its second, yes, second terminal current, so shown here. Then what will be this guy that is required for our calculation? So this is not a general one. This is specifically for our register. So since that is register, the governing rule for our transistors IV characteristics is the Ohm's law. So simply speaking, what we can say is that is given by R. Oh, sorry. R1 and the voltage difference between two terminals. So V of R1's second terminal minus V of R1's first terminal. So that is quite easily obtained from our Ohm's law. Then how about this? R2 and its first terminal. Yes, now we are talking about this current component. Then of course once again we can apply the Ohm's law, so that is given by R2 because this is related to R2, and we have here have V over R2 and its first terminal. So please note that this is not 2, but this one is now becomes 1 minus V R2 comma 2. So this one should be the reference and this one is the measured quantity. So the difference is given by this way. So now, are you happy with all of this calculation? Yes, maybe, but still we have no idea about what is this voltage, what is this voltage, what is this voltage, and what is this voltage. We have introduced 4 different voltages, so we have to also provide information for all of them. So let's just try to do that. For example, the lowest one would be of course R1's first one, and you know that in this case this guy is directly connected to the ground, so its value should be 0. Then how about our the highest one? So V over R2 and its second terminal. Yes, this guy. This guy is connected to, for example, let's say the VDD. Then we will just say this is corresponding to VDD. Okay. Then of course we have to introduce another information about what is voltage for this first resistor and its second terminal, or the second resistor and its first terminal. We have no idea. So actually that is what we wanted to know. But although we don't know the exact value of these two terminal voltages, but what we can say certainly is they should be the same. I mean that yes, R1 its second terminal voltage should be the same with second resistor and its first terminal. Why do we have this condition? So because this is related with connectivity. So they are connected. They are meeting together at a certain terminal. At a certain circuit node. That's the reason why they are in the same voltage. Okay, so connectivity comes in this point. So now think about this one. When you just dump our these values into here and these values into here, now we have 4 different. Now our KCL becomes just on one single equation which is containing 4 different voltages, V1, 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 and among 4 of them, the first one and the last one are just given as a given number, for example 0 or VDD. And now we have the voltages like first register and its second terminal value, and first second register and its first terminal value. However, due to the connectivity, we now understand they are the same. So eventually we will have just one single equation, circuit node voltage, and yes, so now we have one single equation for one single unknown variable, the circuit node voltage. So now the system becomes determined. Okay, so up to now I have just considered a really simple case where we have just two resistors, but point is these discussion can be easily generalized. So what I have done was just to specify the KCL. And of course, KCL need the information about terminal current. So now you can just specify the terminal currents, and additionally, you have to also consider the voltages of each terminal. And for example, if your terminal is connected to a certain voltage source, for example, ground or V in or VDD, then you can just specify that value. Also, for example, for certain nodes, then they are not terminated by the voltage source. So in this case, what you have to do is just to consider connectivity through the circuit node, and just to set all of those circuit nodes uh, to have the same voltage. So that is the general procedure. Okay. So how about our students? Are you all with me on this stuff? Okay, great. However, understanding is quite good, but however, when you really try to implement this one into your code, so maybe that is not that easy. Think about this one. The general situation is now you can have multiple circuit elements, and their connectivity can be quite general. For example, here 1, 2, 3, 1, 2, 3, 4, and 1, 2, 3. So there can be multiple circuit elements, and each circuit element can have multiple terminals, and the number of terminals, that is not that much determined, and their termination can be quite general. For example, yes, let's just connect it to ground and also apply certain voltage, and also apply certain another voltage here, and they can have connectivity, for example, yes, this way, and yes, that way, also another way, even in this way, for example. they can be connected in that way. Also, just changing your circuit, you can disconnect it, and this, instead of that, just connect in that way. That is also possible. So in reality, the implementation of this thing into your system is not that much straightforward. So you have to understand the difficulty of implementing a general net list. So usually in SPICE, this connectivity, circuit connectivity is described by netlist file. It's just describing the connectivity between different nodes and connectivity of different terminals. So yes, that will be specified in this way. But if you are working with quite a simple, you know, quite a simple cases, for example, let's say that if you allow just to have one transistor and one circuit element, then maybe implementation is not that much difficult. So instead of implementing quite much general one, so I just recommend you to just one um, specific configuration, like just one transistor and connected to uh, its drain terminal. We can find a single circuit element. So it can be either a resistor or a capacitor, because inductor will introduce additional difficulty to you. So maybe you can try to implement either R or C, then you can check the result. Okay, so please try to, you have already done your DC simulation with a certain MOSFET, so I wanted to recommend you to first to introduce a certain resistor and connect it to your transistor's drain terminal and change the gate voltage and measure the change of your drain voltage. So now you can calculate it with your single device calculation, and please make a comparison with your result, mixed mode simulation result, with the one calculated from single device calculation. Okay, so up to now, I have explained what is the mixed mode simulation, but eventually I just give you quite a simple homework. So instead of trying to implement really general mixed mode simulation capability, but instead of that, just to consider one circuit element connected to your um, certain terminal. Yes, so that would be enough for your purpose. Of course, if you are serious on this thing, then you have to be careful about the connectivity. So connectivity is the key of your mm, extension to the mixed mode signal. Okay, so are you all with me about your homework? So now you can just introduce an appropriate value of a register, and just to show that your simple circuit, which has just one single transistor and one resistor, can be used as an MOS inverter. So that is my homework today. Okay, so Mr. Bak, your question is actually that was related with my comments. So when you really try to implement your code, so how can you understand which one is connected to which one? That is that requires a general implementation. So that will take quite a long time. So I just give you much relaxed version of this mixed mode simulation. So for example, if your transistor has four terminals and only one terminal is connected to a certain resistor, so let's say that this one, then what you wanted to do is do not modify this this transistor specification. So yes, just to keep it as before. Then now you will have just a solution vector containing your electrostatic potential and electron density and hole density. However, in order to implement this general case, now when you consider, for example, KCL, now you have to understand what is the ID of your transistor. So unfortunately, in this mixed mode simulation, so just specifying potential, electron density, and hole density is not sufficient as a solution vector. So you have to introduce additional quantities like I of your transistors. So there will be different multiple I's, for example, source current, gate current, drain current, and substrate current. And also you have to introduce source voltage, gate voltage, drain voltage, and substrate voltage. Okay, now you have introduced four different quantities for your four terminal device. Then how can you calculate it? So in general, so sum of all of these four terminal current should be zero. So you can introduce one single equation into it. Yes, I sub that should be zero. And also what you can have is, okay, each of them has its own form. Okay, now you can introduce you can introduce these equations. For example, how can you calculate the source current? Then source current is given by the source terminal side integration of your carrier current density and displacement current density. So actually you can follow everything. Yes, in this case you will get the solution for this quantity. Okay, and yes, so in the case of terminal currents, you can easily understand the form you have to have. But point is, now we have to move to this one, these voltages. In the case of voltage, how can you specify the value of your terminal voltages? So this is quite simple. If that is related with a certain voltage source, then just take that value. For example, source is connected to the ground, then you say this is 0. Substrate is connected to the ground, then you say that is 0. And yes, if your gate terminal is connected to a voltage source whose value is V in, then just take V in. And in the case of drain, is it connected to the voltage source? No. So now it requires, yes, it requires certain specification. So what happens, what should be done in this case? That is important question you have to understand. So up to now, let's summarize my explanation up to now. So now when you have n terminal device, then you have to introduce 2 times n unknown variables. So they should be n copies of your terminal current and also n copies of your terminal voltages. Yes, now you can have 2n times unknown variables, and in the case of your terminal currents, you know you have already well defined expressions for your terminal currents. Okay, and in the case of your voltages, you just consider the connectivity. Once that is connected to your voltage sources, then just take that value. However, now only when your certain terminal is connected to another circuit node, then we have to introduce additional consideration. How can we specify the value of VD? Okay. Then now let's go to this terminal, this resistor. In the case of resistor, then what happens? In the case of resistor, if we wanted to be general enough, yes, then just to follow the convention we have just introduced in this case, we can say that the I1, I2, and V1 and V2, they should be specified. Of course, you may say that, okay, Professor, we don't have to have these two different values for I1 and I2, because I1 and I2 always have the same value, absolute value, and should have negative sign or different signs, because sum of I1 and I2 should be 0. Okay, you are right. However, instead of explicitly specifying that or eliminating one of them, let me just introduce this rule. I1 and I2 should be 0. So this is assigned for our one terminal, and we have still another terminal. Yes, in this point we can apply the Ohm's law. What is Ohm's law? So I2 is simply given by V2 minus V1 divided by R. So that is Ohm's law. So of course, if you have, for example, capacitor, then instead of that, you have to say I2 equal to C times D V2 minus V1 divided by, oh, not divided, derivative with respect to the time. So that will be the information we require for terminal currents. So from these two relations, we can completely specify two terminal currents. Then how about the terminal voltage? So V1 and V2. In this case, let's say that we say our second terminal of the resistor is connected to the VDD. Then we can say that, okay, this is VDD. And we know that now we have still one specific case where our terminal, the first terminal, is not directly connected to a voltage source. So its value is not well known. Actually, we have to understand its value. Then what we have to do is just to postpone the the solution of this problem. So everybody can feel that still we have not introduced this KCL. So KCL should be included, and KCL will solve this problem. Okay, for example, yes, this guy and this guy, their value, their voltage value is not determined. Okay, I see. Then maybe you have some temptation that, okay, I will just introduce KCL and say that this V2, for this V2, since that is connected to V1, we will just say that V drain voltage is equal to the resistors the first terminal voltage. That can be a possible solution. But you know that that requires certain priority between elements. So resistor takes the KCL and all other should have just should follow the voltage of our resistor value. So instead of that, we can make a more neutral implementation about that. So how can you do that? In this case, just to introduce another, so another unknown variable. So up to now, all of them comes from what? Comes from our transistor, and these four come from the register, and no unknown variable was assigned for our circuit node. So what I wanted to introduce or suggest to you is just to introduce certain node voltage. Yes, so now let's just say that this is, for example, let's call it as V out. So once we introduce this V out, then now things becomes really simplified. So for V1, what you can do is it is equal to V out. In the case of our VD, drain voltage, also we can say that that should be equal to V out. And in the case of our V out itself, now we can introduce KCL. Then what is the KCL? In this case, what we have to have is, okay, I1 of our resistor and ID of our transistor. Their sum should be 0. So that is all for our implementation for this single resistor connected one. So of course the point is this one. How can we get this I1 and ID? Why we don't have I2? Why we don't have IG? Of course, it is only because this node, out node, is generated from the connection between our R's first terminal and our transistor's drain terminal. So the connectivity information is given here. However, what I wanted to say is, okay, this information, the general treatment of this connectivity information will take quite long for all of our students. So instead of considering this treatment of general connectivity, just to say that drain has some special load specialty, so it has been connected to our circuit element. Okay, so Mr. Park, I think that can be, my explanation can be the solution or answer to your question. So, but your central question, so in the code, how can you consider the connectivity? That is a little bit too complicated. So I just ask you just treat the connectivity as granted and just to use it and implement it. That was my recommendation. Of course, of course, if you are interested, I can just sketch what happens if we are going mm, to the more general implementation. But before starting this final remarks on the general implementation, please confirm that all of you have understood my explanation up to now. So for your homework problem, you can just assume that one single element like a capacitor or a resistor is connected through your drain terminal. That is enough for your homework, and I will explain the more general implementation from now on. Okay, please. No, Mr. Bach. The method you have specified in the chatting log is just one for verification. You have to introduce the coupled system. So in this coupled system, your electrostatic potential, electron density, and hole density, together with these terminal currents and terminal voltages and node voltage, should be all included in your uh, general large system. So please make a coupled system for all of those additional equations and the original DD equations and solve it following the Newton-Raphson method. Then you will get the solution, and please compare your solution with the solution obtained from single transistor. I understand your question as transistor, the DD calculation of transistor that is obtained as a single mode operation. After that, using the load line analysis, you can calculate the IV characteristics of your MOS inverter. That can be another reference data for verification. But your homework itself should be to construct a coupled set of equations, so that it will be the task you have to do. Okay, Mr. Park, could you please confirm you have understood the difference between your question and my homework? Okay. Okay, so since time is quite close to the end, I think that is not possible for me to consider the general connectivity. So I will just wrap up today's lecture, and please prepare this homework problem. I think that this homework problem is important because your term project will be related with this system. So coupled transistor and circuit element system. So and also transient capability is also quite important for your term project. So please implement your system as much as possible. So your term project will be announced on Thursday. Okay, so then see you Thursday. Bye.